Hi everyone, my name is Khashayar and I'm presenting this work on behalf of the team. My today presentation is about fractal pattern effects on natural convection, heat transfer, and flow characteristics. Here is the presentation outline. First, I will talk a bit about the objectives and challenges. Then I will speak about thermal management planning and the factors need to be considered. Next, Smith-Waterhouse counter set fractals and its effects on convection heat transfer will be detailed. And last but not least, heatsink design with Smith-Waterhouse counter set fractals are explained, and the heatsink performance under different operating conditions will be explained. Fractals are a class of complex geometric shapes that have fractional dimensions. Fractal geometries are different from the simple classical or Euclidean geometries and are very efficient in filling space. Fractal dimensions are ideal to describe spatially non-uniform phenomena in nature and are expressed by non-integer values. The fractal concept has gained significant attention in various fields, including power electronic cooling. So on the left, you can see the Sierpinski carpet used in the literature for power electronic cooling. On the right, you can see Smith-Waterhouse counter set fractals introduced for the first time for power electronic cooling. The objective is to try this fractal set for passive cooling system design. And if you compare this fractal to the Sierpinski carpet, you can see this one is much easier to manufacture, design, and the manufacturing cost is less compared to the Sierpinski carpet. The main objective is to try this fractal for passive cooling system design to minimize the parasitic powers and reduce noise by removing moving parts like fan and enhance the system reliability. For thermal management system design, we need to have a reliable software to perform CFD and FEA analysis for this work. We tried SolidWorks Velocity in 2018. The other thing we need to consider is advanced thermal interface material needed to reduce the thermal resistance between the chip or heat source and the heatsink. There are other potential technologies to improve heat splitting performance at the heatsink base plate. For example, liquid microchannel cold plate, but the problem with these technologies, they are expensive and they are not recommended if they are not necessary. For thermal management system design, we need to consider a few factors. We need to have correct understanding of peak heat dissipation rate, the location of heat sources, and the system size and cost. Considering these factors, we make decision whether to design a passive or active cooling system design. We usually aim for less complex system with higher controllability and good dynamic system response. With the implementation of advanced thermal interface material, it is possible to design heatsinks with high cooling efficiencies. With the implementation of appropriate thermal management system, it is possible to keep the chip and printed circuit board temperature under specific limits. And the main target is to avoid thermal runaway. Thermal runaway often leading destructive results and must be avoided. The other issue is with inappropriate thermal management system planning, the device mean time between failure reduces. For example, if you look into the top right, you see the median lifetime versus the channel temperature for an RF chip amplifier. You see for every 10 degrees centigrade temperature increase, the mean time between failures decreases by 50%. And this shows that why thermal management system design is very important. You can see the first 4 iterations of the Smith-Waterhouse counter set in this slide. In this counter set, a smaller piece from the unit segment is cut out with each iteration. For example, in the second iteration, so which is this one, 1/4 of the middle part, and in the third iteration, so the one you see here, 1/16 of the remaining interval is removed. The SPC set is created by repeatedly removing subintervals of VIP1 over 2 powered by n of the remaining interval, and it is nowhere dense. The general definition of SPC fractal can be seen here. The conservation of mass momentum and energy for a steady state natural convection in Cartesian system shown here. The energy equation for the temperature distribution analysis of the heat sink can be simplified as a Laplace equation. Constant heat flux is applied to the base of the fractal fins, as shown here. On the right, you can see the mesh generation in SolidWorks, Fellow's in 2018. The numerical approach is based on locally refined rectangular mesh near the geometry boundaries. Mesh refinement is performed for the case with the most complicated geometry, which corresponds to the 10th iteration of the SVC fractal. So you can find more information about mesh refinement in the paper. This slide shows the fractal iteration effects on the fin mass and the fin effective heat transfer area. So for this case study, we assume that the length of the fin is 10 centimeter and the height of the fin is 5 centimeter. We tried for 3 different thickness, 0.15, 0.3, and 0.6 centimeter. As you see, the fin mass is a strong function of fractal iteration. And on the top, as you see, the fin effective heat transfer area is a function of both iteration and the fin thickness. You see for the thinner fin, the blue one, the fin effective heat transfer area reduces up to the 5 iteration, and then it slightly increases and then become constant. For the thicker fin, the fin effective heat transfer area is reduced up to the 3rd iteration, then it increases. For the 10th iteration, the effective heat transfer area is almost 20% higher than the baseline case, which is the traditional rectangular fin. In this slide, you can see the effect of SVC fractal on convection heat transfer coefficient. On the top left, you can see the SVC with the 1st iteration, which is a traditional rectangular fin. In the middle, you see the SVC with 4th iteration, and the last one is the SVC with the 10th iteration. So we compared the effective heat transfer coefficient along with the section line A, B, and C for each fin, and the results are shown on the right. We don't show the results for the section line C because the heat transfer coefficients are pretty much the same. You can see the results for the section line C in the paper. So in the top right, you see the heat transfer coefficient along the section line A. As you see at the edge of the perforations, the heat transfer coefficient is very high. So, and the average heat transfer coefficient for the 4th and 10th iteration is about 7 to 10% higher than the baseline case, which is the traditional rectangular fin. For the for section line B, you see the results here. As you see, the average heat transfer coefficient for the 4th and 10th iteration is about 10 to 15% higher compared to the baseline case. So it shows how SVC fractal improves the heat transfer coefficient and actually enhances the heat transfer from the fin. This slide shows the fractal iteration effects on the fin effectiveness and the mass normalized fin effectiveness. As you see, for the thinner fin, the fin effectiveness drop up to the 5th iteration, then it slightly increases and then become constant. For the thicker fin, the fin effectiveness dropped up to the 3rd iteration, then it increases gradually up to 10th iteration. And for the 10th iteration, compared to the baseline case, the fin effectiveness is 12% higher. And the main reason because the temperature distribution is more uniform for the thicker fin. For the other 3 fins, for all 3 fins shown on the right plot, the mass normalized fin effectiveness increases. So it shows that how effective is the Smith-Fortrar Cantor set to enhance heat transfer from the heat source. We further investigate the Smith-Fortrar Cantor set, this time with the heatsink design. We try to consider 3 different cases. So for all 3 different cases, the heatsink dimension is pretty much the same. The only difference is the fin thickness and the fractal iterations. So we optimize the number of fins based on the 50-watt heat flux. And the ambient temperature was 20 degrees centigrade. And we assume that the heatsink is placed horizontally. The heat flux dimension is 1.5 by 1.5. The thermal interface material is indium with the conductivity of 80 watt per meter Kelvin. the heatsink material is aluminum 6061. This slide shows the major results. On the left, we can see the overall heatsink resistance. So we increased the heat dissipation rate from 20 to 50 watt in 10 watt increments. As you see for all three heatsinks, the behavior are the same. For the thicker fins, you see that the heatsink performance deteriorates only 1 to 2% for the fractal iterations of 4 and 10. If you look at the right plot, you see that for the thicker fin, the mass reduction is about 25%. So if we combine these results, we see that we can get we can have a high performance heatsink with considerably reduced weight, which is very interesting for the applications like aerospace and telecommunication system. In overall, we tried Smith-Water counter-set fractal for the first time for power electronic cooling. We observed that the mass normalized fin effectiveness improves at higher iterations for all length to thickness ratios examined in this work. We observed greater improvements in mass normalized fin effectiveness for the thicker fin. In the case study we have here, the thicker fin was 0.6 centimeter. The overall heat sink thermal resistance is not affected by SVC for fractal perforations. However, the perforations actually help to reduce the heatsink mass considerably. So as you observed in the previous slide, the heatsink mass can be reduced by 25% for the thicker fin, the fin with 0.6 centimeter thickness. Thank you for your attention, and please feel free to send us email if you have any question. Thanks, and have a wonderful day.